Let's look at the question. Number of connected components in an undirected graph. You have a graph of nodes and you are given an integer n and an array edges where the edges at I is two elements ai and bi in the array, which indicates that there is an edge between ai and bi in this graph, and we should return the number of connected components in the graph. So let's look at our first example. We have n is 5 nodes and edges is 0, 1, 1, 2, and 3, 4. So let's draw them. Node 0 connected with node 1, and node 1 connected with node 2, and node 3 connected with node 4. So 0, 1, 2 form the first component, and 3, 4 form the second component. So it contains 2 connected components. And let's look at our second example. We have n is 5 nodes and edges is 0, 1, 1, 2, 2, 3, and 3, 4. So let's try to draw them. Node 0 connected with node 1, node 1 connected with node 2, node 2 connected with node 3, and node 3 connected with node 4. So 0, 1, 2, 3, 4, it forms a 1 component. So it have only 1 connected component. So in an undirected graph, a connected component is a subgraph in which each pair of vertices is connected via a path. So essentially, all vertices in a connected component are reachable from one another. Let's see, how can we use depth first search to solve the problem? If we run depth first search, it's starting from a particular vertex, it will continue to visit the vertices depth-wise until there are no more adjacent vertices left to visit. Thus, it will visit all of the vertices within the connected component that contains the starting vertex. So each time we finish exploring a connected component, we can find another vertex that has not been visited yet, and we can start a new depth first search from here, etc., etc., etc. So the number of times we start a new depth first search will be the number of connected components. Let's look at the example here. We have 9 nodes and 8 edges, and we want to input them into the solution.count components. If we want to print out the result, we have go back to the beginning and create a new class solution, and then define the count component, which have 2 arguments, n, which is 9 nodes in this case, and edges argument, which will import these 8 edges in this case. And then let's go inside to this function and we create a new variable components. We initialize them to 0 and it will count how many components we have. So finally, we have to return the components variable, and that is the result we want. Let's initialize the hash map array named visited to keep track of the visited vertices. The visited is a 1-element array, 0 multiplied by n. So the 0 represents we never visited before, and the 1 represents we have already been visited. To keep track of the visited vertices, an array of size of O of V space is required. So the space complexity is O of V. And then we initialize visited array, which is 1-element array, 0 multiplied by n nodes. And then we initialize adjacency list array, which is also 1-element array, 0 multiplied by n nodes. So the time complexity is O of V, where V is the number of vertices, which is equal to the nodes. And the space complexity is also O of V. Let's create an adjacency list such that adjacency list at V contains all the adjacent vertices of vertex V. So first, let's create an adjacent list variable, which is an array generated by 1-element array 0 multiplied by n nodes. And then we use a for loop. For I in range of n, we assign empty array into every element of adjacent list. So this adjacent list will contain an empty array. And then we iterate every edges for I in range of lengths of edges. In the ith edge, we append the second node into the first node adjacent nodes array, and we append the first node into the second node adjacent nodes array. And then we use a for loop. For I in range n, we assign an empty list into every element of the adjacency list, and this operation takes O of V times. Let's say we have edges array, which have the edge 1, 2, 3, 4, 5, 3, and 4, 5. And then each node have its own array and represent the neighbor array, which node is 0, 1, 2, 3, 4, 5. So in the first edge, we put 2 into 1's position and put 1 into 2's position. And in the second edge, we put 4 into 3's position and put 3 into 4's position. And in the third edge, we put 3 into 5's position and put 5 into 3's position. And in the fourth edge, we put 5 into 4's position and put 4 into 5's position. And about complexity, building the adjacency list will take O of E time operations as we iterate over the list of edges once and insert each edge into 2 lists. Also, building the adjacency list will take O of E space. Let's use a for loop. For i.e. range lengths of edges, we iterate edges array into the adjacency list. So for every edges I, we have first node and second node. These 2 nodes will form an edge. So in an adjacency list, at the first node position, we append the second node into it. And at the second node position, we append the first node into it. So that is how we generate the adjacency list. And the time cost is O of E times, and the space cost is O of E space. We iterate over each vertex in edges. So if the vertex is not already visited, we just start a depth first search from it. So doing the depth first search to visit it, we add every vertex marked as visited. So during the depth first search traversal, every vertex will only be visited once. This is because we mark each vertex as visited as soon as we see it, and then we only visit the vertices that are not marked as visited. So in addition, when we iterate over the edge list of each vertex, we look at each edge once, so the runtime stack for depth first search will use O of vertices space. So every time when a new depth first search starts, we increment the counter variable by 1. So at the end, the counter variable will contain the number of connected components in this undirected graph. We use a for loop here. For I in range of n, we iterate every node, and if that node is never visited, we increment that component variable by 1, so it will be counted as a new component. Let's try to call depth first search at node I, and we should also add the argument adjacency list and the visited array. And let's try to analyze the complexity. The time complexity is O of vertices time, and the space cost is also O of vertices space. We use a for loop here. For I in range of n, which have 9 nodes, so it will iterate I from 0, 1, 2, 3, 4, 5, 6, 7, 8. Let's check when I is 0. This time the visited at 0 is 0. That means the node 0 has never been visited before. So we increment the components variable by 1, which is become 1 now. Now let's put 0 into depth first search and mark 0 as visited before, and then we check the adjacent nodes of 0, which is node 1 and node 2. Because node 1 has never been visited before, so we try to do depth first search at 1, which have 2 adjacent nodes, 0 and 2. Node 0 is visited before, so we try to do depth first search at node 2, which have 2 adjacent nodes, 1 and 0, but both of them is visited before, so we try to finish depth first search at 2. We finish depth first search at node 1, and we go back to depth first search at 0. The adjacent node 2 is visited before, so we have to finish depth first search at 0. Node 1 has been visited before and node 2 has been visited before, so let's check node 3. Visited at 3 is 0, that means node 3 has never been visited, so we increment the components variable by 1, now it's become 2 now, and then we put 3 into depth first search and mark 3 as visited. We try to do depth first search on node 3, and 3 have only one adjacent node, which is 4, and 4 has never been visited before, so we try to do depth first search at 4, which have only one adjacent node, which is 3, but 3 has already been visited before, so we have to finish depth first search at 4, and then finish depth first search at 3. Node 4 has already been visited before, so now let's check node 5. Visited at 5 is 0. That means node 5 has never been visited before, so we increment the components variable by 1, so now it becomes 3, and then we put 5 into depth first search and mark 5 as already been visited. Node 5 have two adjacent nodes, which is 6 and 7. Because node 6 has never been visited before, so we try to do depth first search on it. It have two adjacent nodes, which is 5 and 8. Because 5 has already been visited before, so let's check node 8. We try to do depth first search at node 8. It have two adjacent nodes, which is 6 and 7. But node 6 has already been visited before, and node 7 has never been visited, so we try to do depth first search at 7. It have two adjacent nodes, which is 5 and 8. But both of them is visited before, so we have to finish depth first search at 7. And then we finish depth first search on node 8, and then we finish depth first search on node 6, and then we go back to depth first search at node 5, but 7 has already been visited before, so we have to finish depth first search at 5. And then node 6 has already been visited before, and node 7 has already been visited before, and node 8 has already been visited before, so all of the nodes already been visited. Then we just return the component variable, which is 3 in this case. That is the result we want. In the class solution, let's go back to the beginning and we try to define depth first search, which have self and argument adjacency list and the visited array and start node, which is to indicate where we should start. In this case, we import I will become our start node, and first we mark the visited at start node become 1, which means it already be visited now. We use a for loop here to iterate every adjacency node of current start node. So if current adjacency node is never been visited, we try to do depth first search on it again, which have the argument adjacency list and the visited array, and adjacency list a start node at I, which is current adjacency node. Now let's try to run our program, which will get the output 3, which is the right result, right? And then let's try to analyze the total complexity. The time complexity is O of vertices plus edges plus vertices, which is asymptotically equal to O of V plus E. And about the space complexity is O of vertices plus edges plus vertices, which is asymptotically equal to O of V plus E too. So that's it.